Welcome back to another video. This is part 2 of the change of variables formula in 2 dimensions. Okay, in the last video we derived why this is true and developed a lot of the key terminology of transformations and the Jacobian. Okay, so let's talk about the procedure we're going to follow and start calculating some examples here. So number one, what should we look at? First, either identify T or the T inverse transformations or mappings. So sometimes I'll give them to you, sometimes you have to come up with them. Okay, and the key here is usually look at the boundary curves, okay? Because what we're trying to always do is look where the boundary curves get sent to boundary curves. All right, what's the next step? Next step, compute the Jacobian of T or the Jacobian of the inverse of T. So why can we compute either one? Well, we've got this beautiful fact from advanced calculus, or also linear algebra in some versions, where essentially the Jacobian of the T inverse is the reciprocal of the Jacobian of T. Okay, and we've got this kind of funky notation here where if you do the Jacobian, the standard one, right, the Jacobian of x and y with respect to u and v, well, you can do the Jacobian of u and v with respect to x and y, but don't forget that sneaky little -1. In this context, that just means reciprocal. Okay, and I kind of like this this blue version that has more bold blue highlighted because I find this one easier to just make less mistakes. Okay, why is this theorem true? Well, this is a deep result in advanced calculus called the inverse function theorem, and it's essentially one of the key tools in differential geometry. So if you're going to study this stuff more carefully, this is a super important result. Okay, just quickly, let me give you some insight as to why these are true. Well, in linear algebra, we call an identity transformation the transformation that does essentially nothing, right? Earlier I wrote f inverse composed with f of x gives us x. This is the same thing as true with t and t inverse. And then the other result is if we do determinants of composition, we can actually just multiply them. Okay, and then the determinant of the identity, again, I'm sorry for not proving any of these things, but when you take linear algebra next semester, or whenever you take it, this is just one of those key things that you'll cover, and you should perk up and be happy that you're like, okay, I remember. There was a really amazing application of this when we did the change of variables formula. Okay, and you can see that basically the determinant of t times the determinant of t inverse, they multiply and give me 1, which is why we do the reciprocal. Okay, another little bit of fine print. This is another reason why we usually require Jacobian of t not being 0, which we achieve by basically saying that it's 1 to 1 and on 2. Okay, another way to think about this is I really like the phrase dimension collapse. Okay, the idea is one way to think about this is think about vectors, right? Two vectors, just simple vectors in the plane. And remember that the cross product was the area of the parallelogram. Well, in order for that area to actually not be 0, v1 and v2 could not be parallel, right? So if v1 and v2 are in the same line, then there's no parallelogram to be constructed whatsoever, which means that the cross product is going to give you the 0 vector, and the magnitude of the cross product will give you 0. Okay, so this is what I mean by dimension collapse, right? Imagine that the angle between the two basically is 0. Okay, so back to our plan here, our procedure, right? So again, this is just this amazing fact. We're going to use this quite a lot actually in the examples. Okay, what's the next step here? Well, once we've got the Jacobians computed, time to rewrite our integral in the new u and v coordinates. Okay, then identify the boundary curves in x and y, and then rewrite them in terms of u and v. And really, there's no specific order to this. You can do this in any order. And again, this is why we either look at t or t inverse. It just depends on the example. There's a lot of flexibility in this method here. Of course, I feel like it's very tough to do these problems without actually sketching d in the xy plane and then sketching d star in the uv plane side by side, just like I showed in the previous videos, okay? And one more thing, I've got these formulas here just to remind you, right? Dx times dy is equal to the Jacobian of t times du dv. Okay, and this is, again, one symbol that people like to use is this double absolute value, where the inside absolute value is the determinant and the outside one is literally absolute value. If you do du dv equals jack of t inverse dx dy, again, just don't forget that the inverse transformation requires the reciprocal, okay? Ask me how I know. I've made that mistake many times myself, so try not to do that. Okay, that's our plan. Okay, example time. So we've got plenty of examples. I might actually just do a couple, take a pause, and then maybe do another video a little later. Okay, so let's start with some linear transformations here. So this is a general procedure that will be kind of nice for you to think about, and also we'll do more of these kinds of things in linear algebra. But all right, let's say we've got two vectors in the u and v plane. So I've got them drawn already for us, and I've got the little smiley face. They're fixed, okay? So what I'd like to do is try to come up with the following transformation, where I'm going to basically predetermine that I want to send I hat, that's, unit vector in the v direction. Oh, what happened to I just noticed something. What a silly person. My u's and my v's got flipped. Okay, anyways, so I hat is drawn correctly, and we're going to send that via t to the vector v1. J hat gets sent to the vector v2. Okay, now I hope you remember this fact. In chapter 12, we basically said, okay, let me use the u and v notation here, but it's a vector in the plane. Well, I can actually split this up as follows using vector addition. Okay, so I'm kind of reverse engineering here, right? U comma 0 plus 0 comma v does indeed add up to u comma v. Okay, at this point, we can also think of scalar multiplication. Pull out the u from the first vector, pull out the v from the second vector, and because we've got zeros there, these are true. Oops. Change that to a 1. Okay, so what I've just shown us is that basically any vector u comma v can be written as u I hat plus v j hat. And again, you kind of do this instinctively by now. So what's next? Well, if I tell you what to do to those two vectors, turns out if I assume two properties of the transformation called additivity, okay, additivity means that first in this calculation, right, we start with u and v, rewrite u comma v as u I hat plus v j hat. So additivity means this kind of plus inside of the parentheses, I can turn it into a plus basically applied to each transformation. Okay, but then we have another property that we require out of linear transformations called homogeneity. What this means is that we can pull out the scalars in front so that the u and the v show up in front here. Okay, since I told you what t does to I hat and t does to j hat, replace those with v1 and v2, and I've got the u and the v in front. Okay, now finally, since I said that v1 was a comma b and v2 was c comma d, put those back in, and then we've got the final form here. Okay, so what I've done here is essentially showed you how to build the linear transformation T that does this property, okay? And the fact that it's linear, just think about it like this for now, right? It sends lines to lines, so it sends basically the square to a parallelogram. Okay, and if you took a linear algebra already, just think of this as we're going to put those vectors v1 and v2 into the columns of a matrix, and that's how we build the matrix associated to a linear transformation. Okay, the key result for me, I just want to emphasize this. The fact that it's a linear transformation, it sends lines to lines, and therefore parallelograms to parallelograms. Okay, I won't prove that generally, but we'll just take this as a fact. I'll prove that in an example in a bit. Okay, so if I throw v1 and v2 into the columns of, actually, I think I'm throwing them into the rows here because, again, I'm doing a cross product calculation. Same results as earlier, and you can kind of convince yourself, okay, if I kind of get rid of the cross product, I can essentially just recover the determinant piece by just looking purely at just that matrix of column vectors, okay? So that is neat here. Okay, what's really remarkable about what I just showed you is that the area of the parallelogram is the determinant of that matrix, which is the Jacobian of T. Okay, so this is one of the most important properties of determinants, is that they really do allow us to calculate areas and volumes of objects, okay? So the other thing to note here is, since AD minus BC is constant, right, that doesn't depend on the U and the V. It's really just a property of the parallelogram. And basically what we're learning here is that the Jacobian is distorting areas in the plane by the same amount everywhere. So that's a super neat result here. Okay, let's do a more concrete application here. So another linear transformation, but this is the one to really pay attention to. So I'm going to do this really slow. I apologize in advance that it's so slow, but I really want this to be the building block to what we're doing with all of these key terms here. All right, so we start off with the transformation T and its pointy bracket. So what this tells us is that x is going to be the function 2u minus v. Y is going to be the function u plus v. So let's start with d star being the triangle with the following three vertices. Okay, and actually, there's a typo here. This should be a 3. So if you got a printout of the class notes and it has a 4, please just change it to a 3. Okay, so let's start by drawing this in the UV plane. Okay, that is 1, 2. Let's draw that first. I'll draw it in pink since I'm in the UV plane. The other point is 2, 1. And the third point is 3, 3. All right, and it did tell us this is the triangle. Okay, so let's just draw these lines connecting these points. So here's D star, very easy, triangle. Let's label this D star. Okay, there's our B4. So now let's try to figure out what D is in the X and Y plane. Again, that's going to be the image of this triangle. So let's start off with just figuring out what T does to just these points. Okay, so I've got the transformation T is over here. Okay, and I've got X and Y, so I want to compute those. So let me just show T of 1, 2, nice and slow here. So it's going to be 2 times U minus V, and then the Y coordinate is U plus V, so 1 plus 2. All right, so what that gives us is 2 minus 2, which is 0, and 1 plus 2, which is 3. Okay, so let's just plot that point in the X and Y plane, so 0, 3. Okay, now what is 2, 1? So this time, let me just start doing this in my head. Okay, so 2 times 2 minus 1, so that's 4 minus 1, that's 3. Okay, and then I add U plus V, so 2 plus 1, also 3. This gives me the point 3, 3. And one more. So what does 3, 3 get sent to? Well, that's going to be 3 times 2 is 6. 6 minus 3 is 3. And then 3 plus 3 gives us 6. Okay, let me clear some space here. Move this over here. Okay, so let's draw that third point, 3, 6. So here is 6. Okay, and what I'd like us to kind of prove is, well, that the image is going to be this triangle, right? So once we've got the 3 points, the thing is, look at this, the functions for x and y, they are linear functions of u and v, so therefore this is a linear transformation, or maybe just look at the title here, another linear transformation. So basically it's going to send lines to lines, okay. And not only do we have the lines to lines, but also it's going to send all of the points inside of the triangle to all of the points inside of this triangle. Cool. So those are the before and after. Let me just label this D. Let's calculate the Jacobian of T next, because this is actually a pretty easy thing to do. I'm going to make it fit up here. So absolute value of the Jacobian of T is absolute value of the determinant of the matrix. Let me just write the formula here. It's xu, xv, yu, yv. Absolute value of the determinant. Now let's calculate these partial derivatives. The partial derivative of x with respect to u is 2. Partial derivative of x with respect to v is -1. Partial derivative of y with respect to u is 1. And the partial derivative of y with respect to v, also 1. Okay, so that is the matrix that we get of partial derivatives. Now let's take the determinant, keeping in mind we multiply the diagonal and subtract the product of the off diagonal. So what do we get here? Absolute value of 2 times 1 minus a -1, so that is 3. Okay, so the Jacobian turns out to be 3. And right before we took the absolute value, we actually got a positive 3. So hopefully I remember at the end here, but I want to talk about what positive determinant actually tells us. Okay, so essentially, if you're doing an example on the test, right? So this is a great place to stop where you kind of figured out what the before and the after are, and this hopefully gives you enough information for how to set up your integral. But here, what I'd like to do is kind of show you the mechanics, the details of how we basically prove stuff. Okay, so let me label the boundary lines here as 1, 2, and 3. Okay, and then let's see where these get sent via this transformation. So let's start with number 1 up here. Okay, and here's how I'm going to do it. Let me just remind you of the point slope formula. From, back in the day. The only twist here is I'm going to basically have the v be my y variables and the u be my x variables. So these are going to look a little funny, but this is all I'm doing. Okay, so here's the thing. Let's start with equation 1. It's just this line. Let me take this point as my point. So I'm going to have v minus the y coordinate, which is v minus 2 equals, let's put a little blank, and then u minus 1. Now, let's figure out the slope. Again, since I'm starting on the left, I know how to get to the next point. I can do the rise over run formula to calculate that the slope is -1 for my rise and then +1 for my run, so that's just -1. Okay, so what is this equation? Well, v minus 2 is equal to -u plus 1. Okay, now at this point, of course, we can do some algebra, but what I'd like us to think about is always take a peek at the original transformations and see if we can draw some insight here. So if we kind of look at these, you'll be like, oh, look at y. Y is u plus v. If I move the u to the other side, I can write this as u plus v on the left and add 2 to both sides. I've got 3. So essentially, this is the equation for the line that is number 1. Okay, cool. Now, because of what I was telling you, right, looking at the transformations, t tells us that this is the same equation of y equals 3. Okay, do we know how to draw y equals 3 in the... Oh my gosh, why is this also a UV plane? How silly. This should be... Let's change these variables here. This should be the XY plane. This is the UV plane. Okay. Clearly copy paste error here. Okay. But onward. Y equals 3. What is that? Well, isn't that just this equation right here? What just happened here? Apologies. Okay, so at this point you can kind of get the idea, but I'm a completist. I want to do everything rigorously. So let's do number 2 next. Okay, so number 2 in the pink UV plane is, well, which point do I want to use in the point slope formula? Let me use this one. And this way I can use that as to help figure out my slope. Okay, for number 2, so v minus, what's my y coordinate? 1 equals blank, u minus 2. Now the slope of line number 2 is going to be go up 2 units, run 1 unit, so the slope is just 2. All right, so that's v minus 1 equals 2u minus 4. And now look at our transformations here. Do they offer any insight? Yeah, look at the x, 2u minus v. So we can play this game again where we move the v to the other side, add 4 to both sides. So 4 minus 1 is 3. Okay, this gives us a way to write our equation for the line number 2, right here. And okay, what does t tell us about this? So t tells us that that line gets sent to x equals 3. Okay, that means let's go to our xy plane. X equals 3, that is just a vertical line. And that's this one. Okay, so I now know where the first curve gets sent. Okay, and I'm using color to kind of signify, right? So pink number 1 is in the UV plane. Blue number 1 is the corresponding curve in the XY plane. Okay. I've got one more for us to do. Let me do that in the middle here. I'm out of space. Do curve number 3. So again, start over here as my point. V minus 2 equals space u minus 1. Now what's my slope? Go up 1 unit over 2 units, so that is rises 1 over 2. Okie dokie. So what do we get here? So v minus 2 equals, actually let's multiply everything by 2 to get rid of the fraction. 2v minus 4 equals u minus 1. And at this point, there's really not much we can do here, because a u and a 2v don't really match up with these transformations. So there's kind of two ways to do this. And let me first show you the kind of the easy way, because you can probably suspect that number 3 on the blue side has to be this curve. Okay, and it's going to be this curve. And in fact, in the blue plane, we can find the equation for this blue line really easily. What is that? That is y equals, what's the slope of this line? So I'm going to go up 3 units, run 3 units, so that slope is 1. And it has y-intercept 3, which we can just see by just staring at it. Okay, so we actually know what this equation is in the x and y plane, and because I know the equation for the x and y plane, in terms of the transformation, what I'm going to do is actually just replace y with u plus v, and replace x with the corresponding function, and hopefully, when I'm done, I get this equation. Okay, so let's work out those details. So number 3 is y equals x plus 3. Now change the variables. Y is u plus v. X is 2u minus v plus 3. Okay, and now let's just start moving pieces around here. So let's subtract u from both sides. So let me check my work here, right? Subtract u on the left, that cancels. Subtract 2u minus u is 1, okay. And then we add v to both sides, so I get 2v on the left, cancels out on the right, and this is my equation, and that is exactly the correct equation in pink. Okay, so this is kind of indirect proof, okay, and if you don't like that, well, here's the other way we can come up with this. So it turns out we can actually construct the inverse transformation here. So let's do x equals y equals, so y is u plus v, x is 2u minus v. Yep, okay, so this is what we call t. So I'm going to build for us t inverse, and it's not going to be that difficult. Now, all it is just solve the same equations, but solve for them in terms of u and v. and the stuff that we'll get on the other side of the equation can only have x's and y's. Okay, here's how we do it. If I just add these equations, what do I get? I've got x plus y. 2u plus u is 3u, but then the negative v plus v cancels out. And solving for u, I get 1/3 x plus y. So that is the first function. Now the second function, we got to work a little bit harder because I got to cancel out the u's. Many different ways to do it, so here's the way I'm going to do it. Take the second equation, multiply everything by 2. So on one side, I'm going to get 2y, 2u, 2v. Yeah, so then subtract the x. What do we get here? So we've got the y side is going to be 2u plus v. Sorry, 2u plus 2v is the 2y minus x. Minus x is going to be minus 2u minus v. Okay, what does that give us? So the 2u's cancel out. And I've got 2v minus a negative v, so that's 3v. And you can see, okay, solve for v, divide both sides by 3, and I've got 2y minus x. Okay, why did I do all of that? Well, let me get rid of this scratch work here. I did it because, remember, we were stuck on equation 3, and equation 3 was 2v equals u plus 3, and I wanted to find out that what the curve that it gets sent to should look like. Okay, and visually we knew it was this line y equals x plus 3, but here's a proof of that. Okay, at this point, go ahead and replace the v with the formula that we derived for in terms of y's and x's. Okay, we got this formula. Replace u with the formula we got. Okay, I'm going to multiply everything by 3. So the 3's cancel on this side. Multiply, or I guess distribute the 2. I'll get 4y minus 2x. On the other side, distribute the 3. This one cancels out, and then I've got x plus y, but then I've got 3 times 3, which is 9. Okay. If I subtract y from both sides, I've got 3y. If I add 2x to both sides, I've got 3x plus 9. Divide everything by 3. Okay, and this gives us curve 3, as claimed. Okay, awesome. So I'm going to pause the video here. See you in the next one.